Hello guys, so this is lecture number 7 under the JEE Concepts, and in this video we're going to look upon the Newton's third law of motion and its related concepts. This video is only about the concepts and we are not going to discuss any question in this video, just some basic questions related to the concepts in between I'm going to discuss. So let us begin. So first of all, Newton's third law of motion. What is this Newton's third law of motion? Well, the statement is if a body A exerts a force F vector on another body B, then B exerts a force minus F vector on A. So this is something like this. Suppose this is body A and this is body B. If this body A exerts some force, say F on this body B, then this body B is going to exert the same force F on this body A but in the opposite direction. That's why minus F over here, like this. So the direction is opposite but the magnitude is going to be the same. But the most important thing to remember about Newton's third law of motion is that forces will never appear together in the list of forces at step 2 that we studied in the previous video of applying equations of Newton's laws. What I'm saying is, like the steps we already discussed in the previous video, the first step was identifying the system, then the second was locating the forces. So when we were locating the forces in the previous video, then that force was only on the system under consideration. Here body A and body B are two different systems. That like body A is a different system, body B is a different system, and these forces are acting on two different systems. So you need to be very clear about this. If you are considering B as a system, then you need to only have this force F in the right direction like this. And if you are considering the body A as the system, then you must have this force negative of F in this direction. So forces will never appear together. So you cannot say that these forces are going to cancel each other in some case, because the forces are only going to cancel if they are acting on the same body. But here the bodies are different, here the systems are different. So you need to consider the forces differently on different systems. This is a very important point about Newton's third law of motion. Second point is, like for Newton's third law, contact between the bodies are not required. But it will not be strictly correct when interaction between two bodies separated by a large distance is considered. So if a very large distance is there in between the bodies and you are considering the Newton's third law of motion, then the correctness of this Newton's third law of motion will not be that much. Like it will not be strictly correct in that situation when the distance between the bodies are so large. And we are going to see it in the chapters of electric and magnetism. But for now, just remember this. Now let us look at the famous horse and the cart problem. Actually, this problem I've taken over here in order to again make it very clear about the system under consideration. That is the step 2 that I've already discussed in the previous video. That what is the importance of considering the system. Suppose in this case we are having two things, like this is what? Cart, and this is what? Horse. Now this horse is basically pulling the cart. So this horse is basically pulling the cart, suppose with a force F1 in this direction. Then according to Newton's third law of motion, this cart is also pulling this horse in the opposite direction. Suppose this F2. And this force F1 and F2 must be equal in magnitude but opposite in direction. So again the question arises, like if this force like F1 and F2 are equal, then how is this whole system is moving ahead with say some acceleration A? How is this possible? This is basically the general way of posing this question conventionally. But as I have already told you the importance of step 2, that is considering the system. So I hope you are getting my point over here, that this force F1 and this force F2 are acting on two different systems. So this is not the whole picture, that if you say that F1 and F2 are equal in magnitude, so this whole system is not going to move with an acceleration A. This is not the whole picture. You need to go in depth. So for going in depth, you need to be very clear about the system. So let us first consider this horse as the system. So while considering this horse as a system, let me consider the mass of this horse as mh and the forces acting on this system. So as I have considered this horse as a system at first, so let me locate all the forces. That is the second step. So if you see the leg, then the normal reaction from this leg will be somewhat in this direction, like N, electromagnetic force, because of the horse applying force on the floor. As a result, the floor also apply force on the horse in this direction, electromagnetic force. And suppose this is making an angle theta, then this N, like the component of this N in horizontal direction will be what? N cos theta, and in vertical direction will be what? N sin theta. But as we are not that much concerned in the vertical direction, then let's only consider this horizontal direction force, that is x direction, and this is supposed to be y. So that is n cos theta, or we can write it as f. Let us consider n cos theta as small f, because suppose if this force is not there, this small f force and cos theta force is not there, then the only force that his horse is having is this F2, and this is the force by which the cart is pulling the horse. So if the net force in this horse will be F2, then the acceleration of this horse will be in the opposite direction, like in this direction, not in this direction in which the whole system is moving with small a. And because of that, then, like because of this F2 force, this horse is going to sit on the cart like this. But this is actually not happening. This is not the case. Horse is actually moving forward, so there must be some force in the forward direction, and that force's magnitude must be greater than this F2 force, and then only this horse is gonna move in the forward direction with an acceleration a. And that's why when we look very carefully, then we have found this electromagnetic force small n in this direction, and the component of that small n force in the horizontal direction is n cos theta, which is small f, because of which this horse is moving in the forward direction. So when you write the equation now for this horse, then this small f minus of f2 upon small mh, capital MH, that is equal to basically the acceleration of the horse. Similarly, this cart will also be having some force in this direction, say n dash, because that I've already considered is n, so this is n dash, and the component of this n dash in the horizontal direction, negative horizontal direction, negative x direction, is say f dash. Then this f1 minus of f dash upon the mass of cart, that is equal to the acceleration a, and these two accelerations are same because this whole system is moving ahead with a constant acceleration small a. So this f1 minus of f dash upon mass of cart must be equal to small f minus of f2 upon mass of horse. These two must be equal because the acceleration is same of this whole system, and for making these two equal, the f dash and f must adjust themselves to make this system move with a constant acceleration a. These two, f dash and f, must adjust themselves accordingly. So this is how you need to see. Just by seeing that f1 and f2 are having equal magnitude and opposite direction, you can't say the system is not going to move. Or just by looking at this force f2 on this horse, you can't say this horse is going to sit on the cart. It is not going to move in the forward direction. You need to show the whole force by considering the system individually. So this is the importance of step 2 that I have discussed in the previous video, that you need to locate the forces very carefully by considering the system very carefully, and then only you can move ahead with the questions. So this is the whole point of discussing this horse and the cart problem. Now let us move ahead. Well, this is again a very important concept regarding Newton's third law of motion, and a lot of questions are going to come with this topic, that is tension in strings. So the general thumb rule of this tension in strings, the only point that you need to keep in mind while doing the questions, is that the tension at all the points in a string is the same provided it is assumed massless. If the string is considered to be massless, then the tension in the string is going to be same throughout, and no massive particle or body is connected in between them. If any massive particle or bodies are connected between the strings, then also the tension in the string is going to vary. So you need to consider these 2 points very carefully. The first one is that the string must be massless, and second thing is that there is no massive particle or body is connected in between them. If there is a massive particle or body, then also the tensions in the strings are going to be different. So let us first consider a very basic question, like I'm considering this as a string and this suppose a mass small m, a block of mass small m. Actually, I am totally referring this whole video from the H.C. Verma book, but I am considering the whole important points of this chapter and discussing it where you guys may face problems. So suppose this is a string and this is some cross section A and this is small m mass. Basically what I'm gonna discuss here is the force distribution by considering different systems. So first of all, let us consider this A and above, like from point P to A, say as a system. So this point P to A as a system. So if you consider this as a system at cross section A, then this whole below part is gonna apply a force, say small t tension, to this cross section A. And I am considering this string as massless in the first case, like here, and this small m block is of mass small m. So if you consider this as a system, then in this system small t tension is there, that is this force small t is there, which is applied by this whole like string and the mass small m. Now if you consider this below part as a system like this, cross section A, then this upper part, like this upper part is gonna apply a force small t according to the Newton's third law of motion. So again you can see that this is another system and this is another system. This is system 1 and this is system 2. So this equal and opposite forces are acting on this two different systems, system 1 and system 2. So you cannot cancel these two forces because the systems are different. Now consider this small m, like how much force is acting on this small m mass. So again you need to consider this as a system and then this as a system. This is system 1 and this is system 2, the small mass m. So first of all I'm considering the small mass m as the system. So this small mass m is having a gravitational force in the downward direction small mg and t dash in the upward direction. Now this t dash will be equal to t because here also we have considered that the string is massless, so the tension is going to be the same because no any mass is in between the strings. No any heavy mass like massive particle or body is connected in between the system. The particle is only at the bottom of the string. So this is small t and this is mg. So from here, as the acceleration of this whole system is 0, so this I can write over here t is equal to mg because this body is at rest. Now if you consider this string as the system, then the only force that is going to act is here small t. This here at this point where this string is connected to the ceiling, here also a reaction will be there, electromagnetic reaction. Say this is small n. Then this small n, this t is going to be equal for making this string at rest. Like t must be equal to n. Because if there is a net force in the downward direction, then obviously this string is going to move with some acceleration. So this force must be balanced out with some another electromagnetic force, and here in this case is small n. So this t must be equal to n. Then only this string is not going to move in the downward direction. Now let us consider a different case in which the string has a mass. Say this is the same string and this is capital M this time, say, and this is cross section A. Now consider is this string having mass small m. So what will happen in this situation, like if I'm considering this as system A, system 1 say, then this will be having forces, say here electromagnetic force n dash and here T1, by which this bottom part is pulling the upper part. Now for system 2, this small mg, the mass of the string, plus T2, the tension in the string, and here it will be this T1, like this T1. According to Newton's third law, if this string is pulling the system 1 with T1, then system 1 is also going to pull this string like system 2 upward with a force equal and opposite, that is T1. So from here T1 must be equal to small mg plus of T2. Now for this capital M mass, this is mg and this is T2. So this T2 must be equal to capital mg. So this is how you need to see. See, because this time this string of system 2 is having mass, that's why I'm considering this T1 and this T2 like tensions different in these strings, because this strings is now having mass. Massless string is having one tension, that is T1, and the string having mass is having another tension T2. So this is how you need to proceed in case of strings having mass. Now let us consider another complicated situation. Say something like this, a pulley having mass small m1 over here, then small m2 over here, then small m3 over here. So how are you going to distribute the tensions now? And I'm considering this pulley is having mass capital M and this whole string is massless. So in this situation, here there will be a tension, say T1, because this is massless string, so it will be same from over here to here, but now this pulley is having mass, so here will be tension as T2, and now here the mass is small m2 and small m3, like massive particle or body is connected in between, so here there will be tension, say T3. So this is how you're going to need to distribute the tensions. Now if suppose this pulley is also having no mass, like this mass is 0, then this T1 will going to be equal to T2, like this T1 will be equal to T2, like this, and this T3 will be different. So this is how you need to see in case of tension in strings, and we are going to discuss a lot of questions on this tensions in string, so don't worry about that now, it will become even more clearer. Now let us discuss about the last concept of this video, that is pseudo force, which is also a very important concept for solving problems related to the non-inertial frame of reference. So far we have just studied about the inertial frames of reference and concepts related to it and questions related to it. But now is the time to study about the non-inertial frames of reference. Well, the one thing that is very important to know over here is that Newton's second law of motion is actually not applicable for non-inertial reference frame. Like Newton's second law of motion is wrong in case of non-inertial reference frame. So we need to adjust Newton's second law of motion so that we can use it while in case of non-inertial reference frames too. And that is where pseudo force comes in. Pseudo force is basically that concept which relates Newton's second law of motion even to non-inertial reference frame, because in actual Newton's second law of motion is invalid in case of non-inertial reference frame. And you already know what is non-inertial reference frame. It is a reference frame which is being accelerated with respect to some inertial frames of reference. So for making it applicable, like for making Newton's second law of motion applicable for non-inertial reference frame, a so-called force called pseudo force is to be included in the list only because we are discussing the motion from a non-inertial frame and still want to use Newton's second law. So let us discuss the concept. So for that, let me consider two reference frame. Say this is A and this is B, and this A is basically inertial frame of reference and this B is accelerating with respect to this inertial frame, and because it is accelerating, so this is non-inertial reference frame. Now I've already considered this as A and this is B, or say this is S and this is S dash. Now I'm letting that the acceleration of S dash with respect to S is A naught vector. Suppose this is accelerating with an acceleration of A naught in this direction with respect to this inertial frame A or S. So this is already given. There is some particle P within this reference frame, like within non-inertial reference frame. This is the case actually I'm discussing, that suppose any particle P is there within this non-inertial reference frame and there is an observer within this reference frame non-inertial which is actually looking at this particle P, and this observer wants to apply Newton's second law of motion to this particle P while being inside the non-inertial reference frame. So how to get the acceleration of this particle P with respect to this non-inertial reference frame which is S dash, that is with respect to this observer within this non-inertial reference frame. So we want to find out this acceleration of P with respect to S dash, that is non-inertial reference frame. We need to find out this and let the mass of this particle P as m. So from relative velocity concept we already know that acceleration of P with respect to S dash, that is equal to acceleration of P with respect to S, that is inertial frame, plus acceleration of S with respect to S dash. That is the thing. Now here, since we know acceleration of S dash with respect to S, so let us put a negative sign over here like this. Acceleration of P with respect to S dash is equal to acceleration of P with respect to S minus of acceleration of S dash with respect to S. And this is nothing but A naught vector, that is already given. Now let us multiply the whole equation with small m mass, that is particle P mass, to get the force expression. Then this m A P S is equal to m A P S minus of m A naught vector. And because of Newton's second law of motion, we already know that F vector is equal to m into A vector. This is according to the Newton's second law of motion, which is applicable only in case of inertial frame of reference. And this is basically acceleration of particle P with respect to S, and this is an inertial frame. So this we can directly write as F vector. So now this term I can write it as acceleration of P with respect to S dash is equal to F vector minus of m A naught vector upon small m. This is basically the expression for finding the acceleration of particle P with respect to S dash, that is a non-inertial frame. So from here you can see that this is not the general kind of equation as we have studied in case of Newton's second law of motion, where acceleration is basically F vector upon m, that is the net force on a particle divided by mass of the particle is basically the acceleration according to Newton's laws of motion, Newton's second law of motion. But here this is an extra term m A naught vector, which is not making this equation to go in the form like this. And from here we can say that Newton's second law of motion is not applicable in this case because of this extra term, because the equation is not matching with the general equation of Newton's second law of motion. So here the Newton's second law of motion is actually violated in case of non-inertial reference frame. So this is the proof of it. So to make the Newton's second law of motion applicable for this non-inertial frame also, we are having this extra term m a naught vector, and this is basically taken as a pseudo force. That is, we are actually considering this imaginary force which is basically acting on this particle p in the opposite direction. Like when this whole non-inertial frame is moving in say positive x direction with an acceleration of a naught, then we need to give a acceleration of negative a naught vector, that is in the negative x direction, to this particle p, or force say small m into acceleration of this whole non-inertial frame with respect to this inertial frame. That is, the acceleration e naught vector is basically with respect to this inertial frame. And so this force, this additional force needs to give to this particle p, and then we can apply this as Newton's second law of motion. So when you also consider this as a force, as a pseudo force, say Fs, then this whole numerator term now considered to be a force divided by mass, and then that is equal to acceleration, which is actually Newton's second law of motion. So we need to take help of this pseudo force for making Newton's second law of motion applicable for this non-inertial frame of reference also. So suppose I am telling that this is a frame of reference, non-inertial one, and this is accelerating with an acceleration a vector, say with respect to some inertial frame. Say this is inertial frame s and this is s dash, and there is a particle say p, and we need to find the acceleration of this particle p with respect to s dash, that is a non-inertial frame, and the acceleration of this non-inertial frame is a vector with respect to this inertial frame. Then this can be written as f vector say minus of m into a vector, and this m is the mass of this particle p. So I have to give a force to this particle p in the negative direction, like in the direction opposite to the acceleration of this non-inertial frame, like this, and we need to subtract it from the actual force with respect to the inertial frame upon the mass of the particle. And this is basically the expression for the Newton's second law of motion in case of non-inertial frame of reference. This will become even more clearer when I'm going to discuss the questions related to the non-inertial frame. So in this video, I've basically discussed three concepts. The first one is Newton's third law of motion, then the famous problem of horse and the cart, then tension in strings. That is a very important thing. And the next video, I'm going to cover the questions on tension in string only. And the last concept is the pseudo force. Then I'm going to discuss problems in the future videos. So this is all about this video, guys. Thank you.